In the summer of 1930, a 19-year-old boards a ship in India bound for England carrying nothing unusual in his luggage. A physics textbook, a reprint of a journal article, a stack of blank paper. 18 days later, somewhere on the Arabian Sea, he will have calculated something that quietly rewrites what a dying star is allowed to become. His name was Subrahmanyan Chandrasekhar, born October 19, 1910, in Lahore, in what was then British India. His father worked as a railway auditor. His mother, self-taught and restless, translated Ibsen into Tamil in her spare time and pushed her son's curiosity from the moment he could read. Growing up, a Nobel Prize wasn't an abstraction in Chandra's family. It was his uncle. Physicist C.V. Raman won the 1930 Nobel Prize in Physics for discovering how light scatters off molecules, becoming Asia's first Nobel laureate in the sciences the same year Chandra graduated college. At Presidency College in Madras, Chandra tore through the physics curriculum, publishing his first research paper before he'd even finished his degree, an unusually confident young mind in an unusually competitive field. In June 1930, Chandra graduated with a physics degree and, almost immediately, something rarer still, a Government of India scholarship to study at Cambridge University, arranged in part by physicist Ralph Fowler, who had read Chandra's early papers from thousands of miles away and wanted him as a student. Leaving India meant leaving nearly everyone he knew for a country that had colonized his own, sailing toward the absolute center of world physics, on a scholarship that would not, in any practical sense, be repeatable if he failed. He boarded his ship in July 1930, bound for Southampton by way of the Suez Canal, a voyage of roughly 18 days, most of it open ocean, with nothing to do but read, think, and write. Packed among his things a copy of Arthur Eddington's landmark 1926 book, The Internal Constitution of the Stars, the standard reference on how stars work, written by the single most famous astrophysicist alive, and the man Chandra hoped, quietly, to one day impress. He also carried a reprint of a 1926 paper by his new advisor, physicist Ralph Fowler, titled simply On Dense Matter, a paper explaining, for the first time, what actually holds up a white dwarf, the strange dead ember a star becomes after it runs out of fuel. A white dwarf is what's left when a star like the Sun finally exhausts its nuclear fuel. Its outer layers puff away, and its core collapses down to roughly the size of the Earth, while still holding on to nearly the Sun's entire mass. The obvious question, if gravity is crushing that much mass into that little space, what on earth stops it from just continuing to collapse forever, all the way down to nothing? Fowler's 1926 answer involved something genuinely new, quantum mechanics. Fowler showed that the star's electrons themselves resist being crushed together, a quantum effect called electron degeneracy pressure, and it holds the white dwarf up with no need for heat or fuel of any kind, indefinitely. But Fowler's original 1926 treatment assumed the star's electrons moved at ordinary, everyday speeds. Chandra, freshly trained in Einstein's special relativity, started wondering what happens to that same pressure when the electrons are packed so tightly they're forced to move close to the speed of light. Alone in his cabin, with no library, no colleagues, and no advisor to check his work, Chandra began redoing Fowler's calculation from scratch, this time building in the relativistic correction from the very first line. Day after day at sea, the equations grew more complicated, not less. The relativistic version of degenerate pressure behaved differently than Fowler's original formula, and the difference wasn't a small correction, it was structural. Then came the staggering result. With relativity built in, the star's degenerate pressure stops rising fast enough to hold back gravity forever. Past a certain mass, there's no equilibrium left to find. The collapse simply doesn't stop. The critical number fell directly out of the mathematics itself, roughly 1.4 times the mass of the Sun. Below it, a white dwarf holds steady forever. Above it, nothing in the physics he was holding says the collapse ever has to stop. Chandra checked the math again, then again. A teenager, alone on a ship, quietly convinced he'd stumbled onto something no one else currently working in stellar physics had yet noticed. He began to sense, even without the vocabulary for it yet, what this number might actually mean, that some dying stars are too massive to ever settle down as anything as calm as a white dwarf. In August 1930, the ship docked in Southampton, England. Chandra disembarked carrying a scholarship, 2 suitcases, and a calculation nobody else alive had yet seen, about to be admitted to Trinity College, Cambridge, the epicenter of world physics. At Cambridge, Chandra finally met his new advisor in person, physicist Ralph Fowler, the very man whose 1926 paper had started this whole chain of thought, now standing in front of him in a Trinity College office. Looming over the whole field was Arthur Eddington, the most famous astrophysicist alive, the man whose 1919 eclipse expedition had confirmed Einstein's general relativity to a stunned world, and the author of the very textbook Chandra had carried on the ship. Chandra showed Fowler both halves of the shipboard calculation. Fowler was genuinely enthusiastic about the first, the clean, relativistic derivation of degenerate electron pressure itself. The second half, the mass limit it implied, visibly made him uneasy. Here's the physics in one picture, the white dwarf mass-radius relation. As a white dwarf's mass increases, its radius doesn't grow, it shrinks. Squeeze in more mass, and the star actually gets smaller all the way down towards zero. A low-mass white dwarf is almost fluffy by comparison, wide, wispy, gently held up. Push more and more mass into the same kind of star, and the curve bends sharply downward. The star keeps shrinking just to hold the extra weight. More mass means more gravity, which squeezes the star's electrons into a smaller volume, which packs them at far higher density. And at high enough density, those electrons stop behaving like Fowler's original, gentler, non-relativistic picture. Here's the balance itself, gravity versus degeneracy pressure, plotted as the star's mass grows. Both curves climb together for a while, degeneracy pressure just barely staying ahead. Then, at a specific mass, the two curves cross. The reason electrons resist crushing at all traces back to a rule from physicist Wolfgang Pauli: no two electrons can ever occupy the exact same quantum state. Pack them tighter, and they're forced into higher and higher energy levels, whether they want to or not. In the non-relativistic picture, that outward push keeps growing quickly enough to match any amount of crushing gravity, no limit required. But once electrons are forced close to light speed, the math changes, the pressure still grows, just not quickly enough anymore. Past roughly 1.4 solar masses, the relativistic version of degenerate pressure simply cannot climb fast enough to match gravity's demands at any radius, however small. There's no stable size left for the star to settle into. Fowler, still Chandra's advisor, remained genuinely unconvinced about the mass limit result, and unwilling to personally sponsor that second paper for publication through the Royal Society in London. Undeterred, Chandra submitted the paper independently to an American journal instead, the Astrophysical Journal, where it was accepted and published, a 20-year-old effectively going around his own advisor to get the result on the record. None of this ended the friendship. Eddington, personally warm toward the young Indian student, invited Chandra to tea, encouraged his broader research, and became, genuinely, if unevenly, something like a mentor. Not everyone in Cambridge shared Fowler's caution. Word of the young Indian student's relativistic mass limit began quietly circulating among Europe's theoretical physicists, several of whom found the mathematics compelling long before most astronomers publicly did. Cambridge gave Chandra a real institutional standing, access to the university's mechanical calculating machines to refine the equation of state, a PhD in the summer of 1933, and election as a Trinity College Prize Fellow that October. Through the early 1930s, Chandra kept refining the calculation across different stellar compositions, and it kept landing in the same place, a mass limit right around 1.4 times the Sun, again and again. Meanwhile, in 1934, astronomers Fritz Zwicky and Walter Baade proposed something wilder still, that some collapsing stars might crush all the way down into a ball made almost entirely of neutrons, an object nobody had ever observed. Almost nobody in 1934 connects Zwicky and Baade's proposal to Chandra's mass limit. But the shape of the puzzle is already there, waiting for someone to notice the two ideas point at exactly the same gap in the physics. Chandra began preparing a complete, generalized version of his theory to present formally to England's astronomical establishment, nervous, because Eddington's personal warmth had never once meant he agreed with where this specific number led. January 1935 arrives. The Royal Astronomical Society's monthly meeting in London is where Chandra will finally present the full, generalized theory in the very room and in front of the very man whose approval matters most. Burlington House, London, January 11, 1935, the Royal Astronomical Society's monthly meeting, packed with the country's leading astronomers, one of the most important recurring gatherings in world astrophysics. Chandra, 24 years old, stands and delivers his complete result, a rigorous relativistic theory of degenerate stars with a firm upper mass limit near 1.4 suns, beyond which, he argues, nothing in known physics halts a collapsing star. By most accounts, the room listens closely and even warmly. A clearly gifted younger physicist, presenting a complete and carefully argued piece of work to the field's most senior audience. Then the meeting's chair calls the next scheduled speaker, Arthur Eddington himself, with a talk titled Relativistic Degeneracy on exactly the same subject, scheduled to follow immediately after Chandra's own presentation. Watching from his own seat, Chandra realizes with dawning alarm that Eddington isn't presenting complimentary work at all. He's about to directly attack the result Chandra just finished delivering. Eddington's technical objection, he insists Chandra had improperly mixed relativistic mechanics with a separate, non-relativistic quantum theory. A dense, confident argument delivered by the single most authoritative voice in the room. Then comes the line that will follow Chandra for the rest of his life. Eddington declares there should be, in his words, a law of nature to prevent a star from behaving in this absurd way. Amusement ripples through the hall. Eddington delivers the line with the easy wit that had made him famous, and 5 years of careful shipboard to Cambridge mathematics gets reduced in a single sentence to an absurdity. Eddington gestures dismissively at the pages Chandra had just presented, arguing the formula simply couldn't describe anything physically real, treating the conclusion itself as proof enough that the method had to be wrong. What Eddington never offers is a rival calculation with real, competing numbers of his own, just total conviction, delivered with the authority of the most celebrated astrophysicist in the world, that nature simply wouldn't allow it. Astronomer E.A. Milne, the era's other towering theoretical figure in stellar physics, publicly sided with Eddington that same day. Two of Britain's most famous scientists aligned against one 24-year-old. Most of the room, deferring to Eddington's fame and charisma rather than working through the mathematics themselves, simply doesn't push back, even though nobody has actually shown Chandra's calculation to be wrong. Here's what was actually at stake that afternoon: the fate of a dying star by its core mass. Below 1.4 solar masses, a white dwarf. Above it, something with no name yet in that room and no floor left to land on. Chandra later described walking out of that meeting hall feeling, in his own words, humiliated, shown up, he believed, as a fool in front of the entire field he crossed an ocean to join. Word of the confrontation spread quickly through European physics circles. Chandra reached out privately to physicists Niels Bohr and Leon Rosenfeld, hoping for a second, more rigorous opinion. Bohr and Rosenfeld told him bluntly they could find no validity whatsoever in Eddington's objection. But neither man would fight Eddington publicly, too occupied elsewhere, and unwilling to pick a public battle with the most famous astronomer alive. Chandra tried again months later at a 1935 meeting of the International Astronomical Union in Paris, hoping the continental physics community might give the work a fairer hearing. Even there, Eddington's reputation followed him. For a young scientist just starting a career, being visibly on the wrong side of Arthur Eddington carried real professional risk, a strong incentive for almost everyone else to simply stay quiet. For the rest of the decade, the dispute simmers, technically unresolved in public, while most working astronomers quietly avoid the subject altogether rather than risk taking a side. Exhausted and disheartened, Chandra begins seriously questioning whether continuing to fight for this one specific result is worth what it's already cost the rest of his young career. In 1936, physicist Rudolf Peierls publishes a rigorous technical paper mathematically defending exactly the physics Eddington had mocked in public, a real, peer-reviewed rebuttal finally on the scientific record. Eddington himself remains completely unmoved. He defends his own position in further papers, and in his own 1935 book, New Pathways in Science, never once conceding the point for the rest of his life. Amid the professional battering, one genuine bright spot, on September 11, 1936, Chandra marries Lalitha Doraiswamy, a fellow physics student from his Presidency College days in Madras, after 6 years of correspondence across continents. Later that same year, Chandra accepts a position at the University of Chicago, arriving in December 1936, effectively easing himself out of Cambridge's inner circle, where one man's public ridicule had made the air permanently uncomfortable. By 1939, astronomers Bengt Strömgren and Paul Ledoux independently confirm and extend Chandra's mass limit calculations, quiet, technical validation that almost nobody outside specialist circles takes much notice of at the time. 4 years after that January afternoon, Chandra has effectively won the argument on pure physics. The public damage from one confident sentence in one crowded room, though, never fully unhappens. Chandra then makes a decision that will define the rest of his working life. He deliberately walks away from white dwarfs and stellar structure entirely, and starts over from zero in a completely unrelated corner of astrophysics. This becomes a genuine lifelong pattern. Stellar dynamics through the 1940s. Radiative transfer soon after, hydrodynamic and magnetic stability in the 1950s and 60s, general relativity and black holes later still. Roughly one entire field mastered, then deliberately left behind every decade. Colleagues later described Chandra's approach as almost monastic, total immersion in one problem for years, a defining book written at the very end of it, then a clean, permanent break to begin again. Some who knew him privately traced this pattern directly back to that January afternoon in 1935. Having been humiliated once for a result he knew was correct, he simply stopped needing the field's applause to keep moving forward. Through the 1940s, based largely at the University of Chicago's Yerkes Observatory in Williams Bay, Wisconsin, Chandra treated his teaching duties in Chicago with exactly the same seriousness as his own research. One semester, his advanced physics course had exactly 2 enrolled students. Rather than cancel it, Chandra drove roughly 100 miles each way, week after week, through Midwestern winters, simply to keep teaching them both. Those 2 students were Sung-Dao Lee and Chen-Ning Yang. In 1957, both would win the Nobel Prize in Physics themselves for disproving the assumed conservation of parity, a full 26 years before Chandra's own Nobel finally arrived. In 1953, Chandra became a naturalized citizen of the United States, having built his entire adult scientific career an ocean away from both Lahore, where he was born, and Cambridge, where he'd been humbled. From 1952 to 1971, Chandra served as editor of the Astrophysical Journal, the same American journal that had once published his mass limit paper when Cambridge wouldn't, raising it through sheer editorial rigor into one of physics' most respected publications. Eddington remained Britain's most celebrated astrophysicist until his death in 1944, having never once retracted his 1935 objection or fully engaged with the physics that had already disproven it. Decades pass. Most working physicists move on from the specific fight entirely. Chandra himself rarely discusses the affair in public, though friends say, privately, the wound plainly never fully closes. The theory Eddington called absurd quietly becomes standard physics. From the late 1930s onward, every serious study of a dying star simply assumes the Chandrasekhar limit is real, without much fanfare and without an apology. What's still missing even now is the one thing that would make the argument impossible to ever relitigate again: actual, directly observed proof that something really does exist on the far side of that limit. That proof, when it finally comes, arrives from a completely unexpected direction. Not from a theorist revisiting old equations at all, but from a young astronomer scanning mile after mile of ordinary chart recorder paper. November 28, 1967, Cambridge graduate student and astronomer Jocelyn Bell Burnell notices a strange, perfectly regular radio pulse buried in months of chart recorder paper, ticking, with eerie precision, once every 1.3 seconds. Within months, theorists identify the source, a rapidly spinning neutron star, the same ultra-dense object astronomers Fritz Zwicky and Walter Baade had proposed back in 1934, now caught for real on paper for the first time. Here's the fate of a dying star chart again, now fully labeled with real objects: white dwarf below 1.4 solar masses, neutron star from there up to roughly 2 to 3 solar masses, black hole beyond that. Chandra's 1935 chart, finally filled in. Then, in the early 1970s, astronomers studying the X-ray source Cygnus X1 find something stranger still, an invisible companion object whose mass is simply too large for any neutron star to hold together. By 1973, most astronomers agree Cygnus X1 must contain a black hole, an object so completely collapsed that not even light escapes it, exactly the kind of endpoint Chandra's 1935 mathematics had quietly implied could exist. The idea still felt audacious enough in 1974 that physicists Stephen Hawking and Kip Thorne placed a formal, wagered bet on whether Cygnus X1 truly contained a black hole. Hawking conceded in 1990 as the evidence became simply overwhelming. Here's the same mass-radius relation once more, unchanged since a ship cabin in 1930, and it's exactly right. Real observed white dwarfs crowd toward that same vertical wall at 1.4 solar masses, precisely where the young Chandra's pencil put it. Every neutron star and stellar mass black hole astronomers have confirmed since is, in effect, a working monument to the exact number Eddington told a packed London hall it was absurd to take seriously. In 1983, nearly 50 years after that humiliating January afternoon, the Nobel Prize in Physics is awarded, split between Subrahmanyan Chandrasekhar and nuclear astrophysicist William A. Fowler. Chandra's half of the citation reads, "For his theoretical studies of the physical processes of importance to the structure and evolution of the stars." The very same white dwarf mathematics Eddington had once mocked outright. Chandra was gracious in public. Privately, though, he was disappointed. The Nobel Committee's language leaned almost entirely on work he'd completed in his early 20s, quietly sidelining 5 more decades of research across half a dozen other fields. Arthur Eddington, dead since 1944, never lived to see any of it. Neither did E. A. Milne, his ally at that 1935 meeting. Both men missed every piece of the data that eventually settled which of them had actually been right. Here's the balance one last time: gravity versus degeneracy pressure, unchanged by half a century of new physics. Past the crossing point, nothing discovered since has ever found a way to make the outward push win again. Chandra remained at the University of Chicago until his death on August 21, 1995, 59 years at the same institution that had welcomed him after Cambridge's most famous physicist effectively pushed him out the door. His name now marks more than one thing: the Chandrasekhar limit itself, NASA's Chandra X-ray Observatory launched in 1999, and an entire generation of astrophysicists who trained directly under him at Chicago. The deeper story here isn't really about one equation at all. It's about what happens when a brilliant, correct 24-year-old collides with an even more famous, completely wrong 52-year-old who refuses, to his own death, to ever admit it. Being right isn't always enough on its own. At the exact moment you're right. Sometimes vindication only arrives decades later, carried by evidence nobody involved in the original argument will ever live to see. Late in life, Chandra described science as something worth pursuing entirely for its own sake, independent of whether the world around you happens to recognize it in time or ever recognizes it at all. Next time you hear neutron star or black hole in ordinary conversation, remember, those categories exist in exactly the form we use them today because one teenager did the math on a ship in 1930 and simply refused to stop believing it. Thanks for being awake and curious with me today. Share this with someone who's ever been told, with total confidence, by someone more senior, that they were simply, absurdly wrong. If this story stuck with you, do two quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments which part of this surprised you the most. I read every single one. Your next story is just one click away. I'll see you there.